I believe we're ready for section 5.2. We're going to start working toward introducing ourselves to the definite integral by looking at area of a region of a positive curve. We're going to look at it first as a sum, and then we're going to see the connection between the sum and an integral. So in my example, I want to look at the graph of y is equal to x squared on the interval from 0 to 2. Our goal is to find the area between that graph and the x-axis, bounded by that vertical line x is equal to 2. So the easiest thing to find the area of is a rectangle. So my suggestion is stick two rectangles in there, and the easiest way to do that is make them equally spaced. So on the interval of 0 to 2, I would just cut up two rectangles like that. And then I have my choice of how to use the height. We're going to have something called a right sum and a left sum. And in my first example, we're going to use a right sum, where we use the right endpoint of each subinterval to make a rectangle. So in the interval from 0 to 1, the right endpoint is at 1. So I find the area of this rectangle here. And then on the interval from 1 to 2, I'm going to find the area of that rectangle. So the height is going to be given by the y value. I've labeled the ordered pair at 2, 4, but when x is 1, 1 squared is 1, so the ordered pair here is 1, 1. The width of each rectangle we're going to denote as delta x. And so for our two rectangles, for rectangle number 1 and for rectangle number 2, we're just going to take the width, delta x, times the height, which is going to be the f of whatever. So I'm going to call this the right sum. Yeah, we're on the right endpoint. So I'm going to take the right endpoint, f of 1, and I'm going to multiply it by delta x. And then f of 2 is the height times the width. F of 1 is the y value and x is 1. And then again, I said delta x was going to be 1 since I cut them up into equal sizes. F of 2 is going to be 4, and delta x is 1. So I have 1 plus 4. My first approximation to the actual area is 5. But that's quite an over approximation because you can see how much those rectangles hang out of the region. So next, I'm going to use the left endpoint and make blue rectangles here. The first rectangle won't even have much of a height because the left endpoint is at 0. And then the right endpoint is here. So for these two blue rectangles, I'm going to have my height is f of 0 times my width plus f of 1 times my width. And I get 0 times 1 plus 1 times 1, so I get 1. So now my impression is that neither one of those are good indicators of what the actual area is, because I have so much inscribed with the blue rectangles and so much circumscribed with the red rectangles. So maybe if we double our efforts and cut up our intervals into 4 pieces, so now each delta x is going to be a half, and then find the left endpoint and the right endpoint there. So let's kind of make a number line here. Let me kind of put the graph. I didn't leave myself a heck of a lot of room. So let's just go up here. So I've got the interval from 1 to 2. So here's one rectangle. Now I'm going to cut it to a half, and then 3 halves. And with right endpoints, I'm looking at these rectangles here. Okay, so the idea is delta x is a half. The right endpoints will be at f of a half. I'm going to factor out the delta x. So I'm going to have f of 1/2 for rectangle 1 right here. F of 1 for rectangle 2 to be the height. Then f of 3 halves. And then f of 2. All of that multiplied by that common factor of delta x. To get the y values, I have to plug them into the equation. Y is x squared. So f of 1/2 is 1/2 squared, which is a fourth. 1 squared is 1. 3/2 squared is 9/4, and 2 squared is 4. So I have 10 of all of that times a half. So 10/4, which is 5/2, that's 2.5, plus 5 gives me that approximation is 7.5. If I use left endpoints over here, my left endpoints will be from there, and the first rectangle will have a height of 0, and then the other one, and then this left endpoint, and then that left endpoint. So I'm going to get some numbers smaller than 1, but I will need to find, I'll do it in red here, f of 0 plus left endpoint will be f of 1/2, and then f of 1, and then f of 3/2. All of that multiplied by delta x. So f of 0 is 0, f of 1/2 was a fourth, f of 1 is 1, f of 3/2 is 9/4. Oh, I don't think I multiplied by a half in the previous. I'll come back and do it. So I have 10/4, which is 10/4 is 5/2, or 2.5, plus 1 is 3.5. So I have to multiply that by a half. And then I need to back up. I didn't think I multiplied this by a half, but let's check. That's 10/4, or 5/2. That's 2.5, 3.5, 4, 5, 6, 7.5, and then I have to multiply that by 0.5. So let's go ahead and do this. 5 times 5 is 25, 35, 36, 37. So 2 decimal places gives me 3.75 is that area. And then here in red, 5 times 5 is 25, 3 times 5 is 15, 16, 17, and 2 decimal places. So now the claim is the actual area is some number between 3.75 and 1.75. So what we would do is we would keep improving our approximation. We would do maybe 8 rectangles, 16 rectangles, maybe multiples of 2 like that. So we're going to continue with this general scheme. We're going to keep cutting this up into more and more and more and more rectangles. And as we keep doing these, the rectangles get skinnier and skinnier. And whether we used left endpoints or right endpoints, it's not going to matter. So we do this for infinity until our rectangles are infinitely thin. And it looks like I'm just kind of coloring in this area. So in general, if you want to find the area beneath a continuous function, instead of doing this forever, we use a limit. We take these little widths to get smaller and smaller and smaller. And as we do that, the number of rectangles is going to go to infinity. So we get more heights to add times smaller widths, where we can get the widths by taking the length of the interval and dividing it by however many rectangles we plan to put. So instead of doing this by brute force, we're going to do it using the calculus concept of a limit. We're going to do it algebraically. Now, just like finding derivatives with the definition, this is not going to be the actual way we're going to find areas. This is just the idea behind it all. So I'm going to show you how to do this with a limit. I've taken this sum that I've written here, and I wrote it using summation notation. The Greek capital letter sigma means we're going to add things that look like f of a plus something times delta x, where that something is a counter. K goes from 1 to n. So here k is 1, 2, all the way out to n. So that moves us down. It looks like we're using right endpoints when we write that. But again, it's not going to matter because our delta x's are going to get real small. So it's the height times the width as the number of rectangles goes to infinity. And that's something called a Riemann sum. Now when we do this in general, we're going to have a function of n, and we're going to then let n go to infinity using our ideas of how to calculate limits to infinity. So it might be helpful to use these 4 basic summation formulas if we've got some easy function like a polynomial, which are my examples. The first one says that if you add 1 to itself n times, then 1 plus 1 plus 1 plus 1 n times is going to give you the number n. The sum of the first n counting numbers is n divided by 2 times n plus 1. For instance, if you add the numbers from 1 to 4, here n is 4. If I add it by brute force, 4 plus 3 is 7, 8, 9, 10. If we use this formula, 4 divided by 2 is 2. 4 plus 1 is 5. 2 times 5 is 10. So it does hold if you try it with a small amount of numbers. The other 2 formulas, you're just going to have to believe me. The sum of the first n squared numbers, 1 plus 4 plus 9 plus 16, all the way out, blah, 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 looks like n times n plus 1 times 2n plus 1 over 6. And the sum of the first n cubed numbers has the form of n squared times n plus 1 squared over 4. I'm not lying to you about any of those. They're in your book, but I'm going to show you how they pop up. I'm going to do this same problem, but I'm going to do it in general. I'm not going to do 2 rectangles, 4, 8. I'm going to do n rectangles. So my goal is to form sums that look like f of a plus k delta x. In our example, AB, we were using from, let me go back here and look, we were going from 0 to 2. So our AB here is from 0 to 2. So A is 0, and then to get delta x, we take b minus a divided by n. So we start that way. Delta x is b minus a over n. Our b is 2, a is 0. So our delta x, every rectangle has a width of 2 over n. And so our sum is going to look like the sum from k is equal to 1 to n of f of a plus delta x times delta x. So for here, that's going to look like the sum from k is equal to 1 to n. Our function was x squared plus 1. A is 0. So we're going to have 0 plus delta x, which is going to be f of 0 plus 2 over n, because delta x is 2 over n, times 2 over n. All right, so to get this, we put 2 over n where the x is. So we have 2 over n squared plus 1. That's f of 2 over n. Then we multiply that by 2 over n. Oops, I need a k here. So I need a k here. K times delta x. There it went. About lost that. That would have been drastic. Okay, now we're going to simplify that. When I simplify that, I'm going to get 2 squared is 4, k squared over n squared plus 1 times 2 over n, which I now break that up. I'm going to multiply through by the 2 over n. So that gives me 8k squared over n cubed plus 2 over n. We can break that up. You can add things in any order, so I'm going to add them by taking the 8k squareds over n cubes, and then I'm going to add them to 2 over n. Now let's come up here. I'm going to take out the things that don't have anything to do with the k. So in the first batch, I have an 8 over n cubed times the sum of the k squareds. And then I take out the 2 over n, and that leaves behind a 1. Those are all k is equal to 1 to n. Okay, now I'm going to go up there and go grab the formula for the sum of the k squareds. the sum of the k-squareds looked like n plus 1, 2n plus 1, all over 6. And the sum of 1 added together n times was just going to be n. So then I have plus this 2 over n times n. And so when I simplify, I've got, well, I don't want to multiply all this out. I'm going to have 8 n plus 1, 2n plus 1 over 6n cubed, and here the n's cancel. There's our expression in terms of n. Now the next thing we have to do is take the limit as n goes to infinity. That makes the delta x's real small. As n goes to infinity, this 2 stays at a 2. And the expression in the parentheses here, I'm going to have an n times a 2n times an 8. So I'm going to have a 16n cubed over 6n cubed. And since the powers are the same, I should just get the coefficient. Well, 16 over 6 is 8/3. 2 is 6/3. So I should get 14/3 as the actual area. Hang on to that number because we're going to come back and I'm going to show you some magic. All right, so let's use it again. I'm going to first do little by little. Here is just a straight line. So let's graph it. Okay. Two x plus 1. When x is 0, I'm out here at 1. Whoa, Nelly, let's get out of here. And when x is 3, 2 times 3 is 6 plus 1 is 7. Let's just put that right here. So it looks something like that. Okay. All right. So starting with this, we're going to say let's make 6 rectangles. Okay, so if n is 6, then delta x is b minus a over n. So 3 minus 0 over 6 gives me each rectangle is a half a unit apart. So here are 6 rectangles. And in part A, we want to use right endpoints. So they'll look like this. So my first right endpoint is a half, then 1, then 3 halves, then 2, then 5 halves, then 3. And delta x is a half. So remember we're doing the sum of our f of x's times our delta x, base times height. The base is delta x, the height is f of x. So I'm going to do f of 1/2, let me factor the delta x like I did before, plus f of 1 plus f of 3 halves plus f of 2 plus f of 5 halves plus f of 3, and then all of that multiplied by 1/2. To get the f's, we put those numbers in where the x is, 2 times x plus 1. So 2 times 1/2 plus 1 plus 2 times 1 plus 1 plus 2 times 3 halves plus 1 plus 2 times 2 plus 1 plus 2 times 5 halves plus 1 plus 2 times 3 plus 1. Then we take all of that, multiply it by 1/2. So let's do the number crunching. 2 times 1/2 is 1 plus 1 is 2. 2 plus 1 is 3. 2 times 3/2 is 3 plus 1 is 4. Then I have 5, then 6, then 7 times 1/2. And so we're going to get, let's see, 7 and 3 is 10. 6 and 4 is 10, so that's 20. 27 over 2. About, what is that, 13.5? Okay, so that's part A. That's the right sum. In part B, the left sum, the only difference is we start at 0, and our rectangles are going to be these red ones. They're going to be an underestimate because these are all under the graph. And so for those rectangles, I'm going to do it in red, we'll have f of 0 plus f of 1/2 plus f of 1. Keep going by halves. Now I've got all 6 of my rectangles' heights, then I multiply by 1/2. So I have all of these numbers. Those are these guys. Throw in f of 0, which is 1. So it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 times 1/2. So that's 7, and 7 is 14, 21 over 2. So this one is about 10.5, the other one was about 13.5. So next I'm going to do it in general, using the summation formulas and n rectangles. So in the next part, B is 3, A is 0, so with n rectangles, delta x is b minus a over n, so it's just going to be 3 minus 0 over n, which is 3 over n. Okay, and my plan is to write the sum of f of a plus k times delta x multiplied by delta x. Let k go from 1 to n, and then take the limit as n goes to infinity. A in our example is again 0, and delta x is 3 over n. So we're going to look at taking the limit as n goes to infinity of the sum of f of 0 plus k times 3 over n times delta x, which is 3 over n. So we want the sum of f of 3k over n times 3 over n, with the limit in front. F in this example was 2 times x plus 1, so 2 times 3k over n plus 1 is our f of 3k over n times 3 over n, with the summation symbol with the limit. Now we simplify. 2 times 3k over n gives me 6k over n plus 1. Next we distribute the 3 over n. 3 times 6k is 18k over n squared plus 3 over n. The sum is on k. So I'm going to take out everything that doesn't have a k on it and break my sum up. So I'm going to first factor out the 18 over n squared. Then I have the sum of k. Then I factor out the 3 over n and have a sum of 1. Now we go back and grab those formulas. The sum of k from k is equal to 1 to n is n over 2 times n plus 1. And the sum of 1 from k is 1 to n is n. So I'm going to fill that in. This one is n over 2 times n plus 1 times the 18 over n squared. Sum of 1 gives you n. And now if I multiply this out, 2 goes into 18 9 times. Let me go ahead and reduce there. Then I'm going to have an n squared plus n and an n squared down here. And then here the n's cancel. Now when we take the limit as n goes to infinity, I have the same power, so I just get the ratio of the coefficients, and then the 3. So the actual area is 12. Okay. Now we can get that area using geometry. This is a trapezoid where one base has length of 1, one base has length of 7. The area of a trapezoid is the 1/2 base 1 plus base 2 times that length there, 3. So if I did this using the area of a trapezoid formula, 1/2 of 1 plus 7, then multiplied by 3. So by geometry, the actual area is 1/2 base 1 plus base 2 times the height. So 1/2 1 plus 7 times 3. 1 plus 7 is 8. Half of 8 is 4. 4 times 3 is 12. It's nice to know that calculus agrees with geometry. Now comes the really exciting part. Everything that we've done in these two examples can be done with an antiderivative. Let's start with our last example, the antiderivative of 2x plus 1. Antiderivative of 2x is x squared, antiderivative of 1 is x, plus some constant of integration. So let's call that capital F. Now the limits or the numbers that we went from x is 0 to x is 3. So I want to find f of 3 minus f of 0. F of 3 is 3 squared is 9 plus 3 plus c. F of 0 is 0 squared plus 0 plus c. And look at there, we get the same 12 that we got a second ago. Now let's go back to our very first example, which was just y is equal to x squared from 0 to 2. So our first example, f of x is x squared on 0 to 2. So we're going to compute the antiderivative of x squared, and you're going to get 1/3 x cubed plus c. Let's call that capital F. And then we want to find f at the right endpoint minus f at the left endpoint. So you have 1/3 times 2 cubed plus c minus 1/3 times 0 cubed plus c. So that's 8/3 plus c minus c. So we should get 8/3. Is that what I got up here? Where did it go? Where did we do that? I got 14/3. What on earth did I do wrong? Oh, this was plus 1. My bad. I got to do the plus 1. Let's get back here and get that plus 1 on there. So that'll have a plus x. So let's rub that out and fix all that. Okay, so f of 2 will be 1/3 times 2 cubed plus 2 plus c. F of 0 is 1/3 times 0 cubed plus 0 plus c. See, the c's aren't going to matter because they're always going to subtract out. This is all 0. So this is 8/3 plus 2, 8/3 plus 6/3. There, by gosh, by golly, is the 14/3 I got before. So there's the tie between this area as an infinite sum and the integral. See, this integral sign looks like a sum, a S, and it's going to find us area. And so I'll talk about that in section 5.3.